On the last video, I said we were going to look at more examples. I lied. We're actually going to look at some theorems and some proofs of some theorems. Right. So our theorem here we have is every convergent sequence is bounded. Right. So if we have a sequence and that sequence is going to something, then it is bounded. So when you look at the absolute values of all of the terms of the sequence, there is some value of m that they are all smaller than. Right, so let's prove this. So let our sequence S sub n be convergent. So if that value of S sub n is convergent, and let's say it converges with S sub n going to this value of S. So if we have this convergent sequence, let's go through and let epsilon be equal to 1. So if our value of epsilon is equal to 1, then there exists a natural number such that the difference between the nth term and the value it's converging to, which we had said was S, that we are within at least 1 unit of S whenever we are large enough. So whenever little n is at least big N. Thus, we could say that the absolute value of S sub n is less than the absolute value of S plus 1. And why could we say this? Well, we can say this is true for n bigger than big N. And that's true by an exercise we did before. Right? So exercise 3.2.6b. Right, so we know that is true. So let's let m, big M, be equal to the maximum of S1, the absolute value of S1, S2, up through the absolute value of S sub big N, along with the absolute value of S plus 1. So if M is the largest of all of those choices, then we have the absolute value of S sub n is less than or equal to big M for every single n in N. So by our definition of boundedness, S sub n is bounded. All right, we'll take a look at the next theorem in the next video.